The paper of the day is Paxos Made Live, an engineering perspective. Paper described implementation of a fault-tolerant database based on the Paxos consensus algorithm. Despite the large body of literature in the field, algorithms dating back more than 15 years and experience of our team, it was significantly harder to build the system than originally anticipated. We attribute this to several shortcomings in the field. There are significant gaps between the description of the Paxos algorithm and the needs of a real-world system. In order to build a real-world system, the expert needs to use numerous ideas scattered in the literature and make several relatively small protocol extensions. The cumulative effort will be substantial and the final system will be based on an unproven protocol. The fault tolerance computing community has not developed the tools to make it easier to implement their algorithms. The fault tolerance computing community has not paid enough attention to testing, a key ingredient of building fault tolerant systems. Looking at some highlights, while Paxos can be described with a page of pseudocode, our complete implementation contains several thousand lines of C++ code. The blow-up is not due to simply the fact that we used C++ instead of pseudo notation, or not because our coding style may have been verbose. Converting the algorithm into a practical production-ready system involved implementing many features and optimizations, some published in the literature and some not. It's a great read to help temper over-enthusiasm before you leap into creating your own implementation of a consensus algorithm. The authors report their experiences in three categories: algorithmic gaps in the literature, software engineering challenges, and unexpected failures. They also include a brief overview of Paxos and multi-Paxos. We'll skip those given we have spent the last 2 days looking at the protocol, but you might find it helpful to read through this part of the paper as the ideas are explained using slightly different terminology, and seeing them through the another lens can help take their place. Algorithmic challenges. While the core Paxos algorithm is well described, implementing a fault-tolerant lock based on it's a non-trivial endeavor. Disk corruption. The first issue the team had to deal with was the possibility of disk corruption. It happened and will happen again. That is, when a replica's disk is corrupted and it loses its persistent state, it may renege on the promise that it has made to other replicas in the past. This violates a key assumption in the Paxos algorithms. That is, checksums were introduced to detect changed file contents, and marker files were used in Google Distributed File System, that is GFS, to be able to distinguish between a replica's disk becoming completely empty due to a fault and a brand new replica. A replica with a corrupted disk rebuilds its state as follows. It participates in Paxos as a non-voting member, meaning that it uses the catch-up mechanism to catch up but does not respond with a promise or acknowledgement messages. It remains in this state until it observes one complete instance of Paxos that has started after the replica started rebuilding its state. By waiting for the extra instance of Paxos, we ensured that the replica could not have reneged on an earlier promise. Master leases. When the basic Paxos algorithm is used to implement a replicated data structure, reads the data structure require executing an instance of Paxos. This serializes the read with respect to updates and ensures the current state is read. In particular, read operations cannot be served out of the master's copy of the data structure because it is possible that other replicas have elected another master and modified the data structure without notifying the old master. In this case, the read operations at the master runs the risk of returning stale data. Since read operations usually comprise a large fraction of all operations, serializing reads through Paxos is expensive. Continuing on master leases, to solve this, a leasing mechanism is introduced such that when a master has a lease, it is guaranteed that the other replicas cannot successfully submit to Paxos. This means it can serve a read locally. The team also introduced a mechanism for boosting the master sequence number periodically to avoid frequent master swapping with intermittent network outages. Epoch numbers. In Google's application, Chubby needed to know when leadership, that is, membership, was lost and reacquired during the handling of a result. So they introduced a global epoch number with leadership changes, demarcating epochs. Paxos made simple points out that Paxos itself can be used to coordinate group changes, while group membership. Core Paxos algorithm is straightforward. The exact details are non-trivial when we introduce multi-Paxos, disk corruptions, etc. Unfortunately, the literature does not spell this out, nor does it contain a proof of correctness for algorithms related to group membership changes using Paxos. We had to fill in these gaps to make sure the group membership work in our system. To avoid the problem of an ever-growing log, periodic snapshots were introduced with the ability to recover from a snapshot after failure and then replay the rest of the log from there. This mechanism appears straightforward at first and is mentioned briefly in the literature. However, it introduces a fair amount of complexity into the system. The persistent state of a replica now comprises a log and a snapshot that have to be maintained consistently. The log is fully The log is fully under the framework's control and the snapshot format is application specific. Some of the subtle issues with the snapshot include coordinate snapshots and the log, taking a snapshot while the replica's log is still moving forward, failed snapshots, and the snapshot that occur during recovery. Looking at software engineering challenges, fault-tolerant algorithms are notoriously hard to express correctly even as a pseudocode. The problem is worse when the code for such an algorithm is intermingled with all other code that goes into building a complete system. It becomes harder to see the core algorithm, to reason about it, or to debug it when a bug is present. It also makes it difficult to change the core algorithm in response to a requirement change. The team solved this issue by creating a state machine DSL and compiler to translate the DSL into C++. The language was designed to be terse so that a full algorithm could be rendered on a single screen. Extensive runtime self-checking mechanisms were also introduced, including checksum database log comparisons. The testing harness takes the system through a long sequence of failures and verifies that it still behaves as expected. Our test starts in safety mode and inject random failures into the system. After running for a predetermined period of time, we stop injecting failures and give the system time to fully recover. Then we switch the test to liveness mode. The purpose of this liveness test is to verify that the system does not deadlock after a sequence of failures. Even with the state machine DSL and extensive runtime checks, the test harness still found bugs. This test proved useful in finding various subtle protocol errors, including the errors in our group membership implementation and our modifications to deal with corrupted disks. In order to measure the strength of this test, we left some protocol bugs found during code and design reviews in the system and verified that our test system detected these bugs. After a number of bug fixes, the test became very stable. In order to improve its bug yield, we started running this test on a farm of several hundred Google machines at a time. We found additional bugs, and some of which took weeks of simulated execution time to find. Unexpected failures. With over 100 machines years of execution in production, the number of failures was impressively low, but still higher than the Google team would like. In 2015, some of the reported failures don't seem so unexpected. Problems with rollback and upgrade scripts that weren't fully automated and regularly tested. We now rely on carefully written and well-tested scripts to automate rollout and minimize operator involvement. As a result, our most recent major release of Chubby was rolled out across hundreds of machines without incident while serving live traffic. Here's the conclusion. There are significant gaps between the description of the Paxos algorithm and the needs of a real-world system. In order to build a real-world system, an expert needs to use numerous ideas scattered in the literature and make several relatively small protocol extensions. The cumulative effort will be substantial and the final system will be based on an unproven protocol. For anybody who has ever tried to implement it, Paxos is by no means a simple protocol, even though it is based on a relatively simple invariance. This paper provides imperative pseudocode for the full Paxos or multi-Paxos protocol without shying away from discussing various implementation details.